Hey guys, welcome back to inequality topics. So we were considering linear inequality in previous videos, and we discovered how to find the region that is defined by a set of inequalities. And actually we found out how to solve the inverse problem. So inverse problem, when you already set up the region, and for that region you need to set up an appropriate set of inequalities. So basically you need to describe this region in terms of mathematics. So set up inequalities and which fits to that region. Okay, so here, and as in many problems for GCSE and high tier, so you are asked to find only points with integer, basically integer coordinates, so sometimes called integer points within the region. So amongst all the points, because actually if you define the region and this region is not a single point, you understand there are really an infinite number of points within that, right? So let's say you have a triangle, you have a quadrilateral as a region, but you understand that there are infinite many solutions for as in terms of points. In this case, you're asked only about points which have only integer coordinates. So that those points are called integer points. Okay, so and sometimes you might be asked about like some function. You're given equation with a function, and you need to define the maximum or minimum value within those integer points. Okay, so let's have a look at the problem. That's typical problem. I try to combine as many as possible questions here. So first, the first question asks you to graph the region R defined with inequalities. So and you set up inequalities: x more equal than 0, y more equal than 0, x plus y less or equal than 8, and 2x plus y less or equal than 12. As you can see, all the inequalities are linear, so that's the standard task and standard direct problem. Okay, so the second part asks you about how many points in that region are that you set up before and from the first problem will have integer coordinates. Okay, so you basically need to say how many points, you need to count the points within the R with integer coordinates. That's the primary focus of that video. Okay, so problem 3 asks you find all integer coordinates x and y such that 2x plus y equals 12. So x and y from the region R. Okay, so we are always talking about that region that you define, that you were that you defined in the first problem. Okay, so the problem 3 asks you about find all integer coordinates such that 2x plus y equals 12. So basically it asks you about find all the points that lie on this straight line with the given equation. All right, and problem 4. This is about maximum value for a given expression. So basically this function might be called 2x plus 3y. It might be called as the target function, basically objective function that is supposed, or the function that is supposed to be optimized. Okay, so you need to find the maximum value for that expression 2x plus 3y, where xy from that region, of course, with the integer coordinates. Okay, so you need to find max values of that objective function 2x plus 3y, where x and y set of coordinates from R and they are integers. Okay, so guys, try pause the video if you really know how to do each part. Pause the video, try to do by your own, and here I'll start with explanation. All right, so I just move to the next slide and try first to solve the first part of the question. So graph the region R defined by the inequalities. So I just simply transfer that all those inequalities here. So we set up x more or equal than 0, y more or equal than 0. We've got x plus y less or equal than 8, and 2x plus y less or equal than 12. Okay, so we've got a set of inequality, and we're going to draw the region on Cartesian plane. So here's, you need to be as much accurate as you can, because this is about how accurately you're going to draw your linear graphs, basically straight lines. Okay, let it be so. And we've got y and x-axis. And first, what I'm gonna do here, I'm not gonna shade, I just only show you using by arrows. Arrows will be indicate the region part that actually fits up to our inequalities. And first, I'm wondering about that line, x more equal than 0. So the line x equals 0 is basically the vertical line, y, in this case y-axis, and more equal than 0, so that region that we are interested in. So that's why I can set up x equals 0. That's an equation of that vertical line, so that region is here. So I can set up even that region with the blue lines. Okay, so it goes down obviously infinitely, but so I'll indicate that we're interested in that region, which is on the right side of that, so actually there. Okay, so next part, y more equal than 0 is pretty easy. So y equals 0 is simply this level, and which coincide with x-axis. So that's why I put corresponding segment here to indicate the boundary. It's right there. And actually, again, indicates the region that we satisfy according to that inequality, y more equal than 0. So the region is just above x-axis. So here, that way. Okay, right now, so we have two inequalities that describe the first quadrant, okay? Quadrant, which is here. Okay. So next one, x plus y less or equal than 8. So first I'm going to turn into the equation, first of all, to set up the boundary. X plus y strictly equal to 8, and that means this is definitely an identity line starting with 8 as y-intercept. So if you want it, you can rearrange into into the gradient intercept form, but you can also set up the table for that line. Let's say this is line 2. Now in this case line 3, so we set up line 1 and line 2. So that's basically line 2, that's line 1, and now we're having to deal with line 3, x plus y equals 8. So I can set up this table values for x and y. So but I know that when x is 0, y equals 8, and vice versa. When y is 0, x equals 8. So this is definitely an identity line, but it's shifted by 8 units up. And it goes with a negative slope. If you transfer x to the right side, you can see that y equals to negative x plus 8. So I put that line here, but before I want to mark 8 marks on x and y axis. So 1, 2, 3, 4, 5, 6, 7, 8. So here is 8, and the same for y direction. 1, 2, 3, 4, 5, 6, 7, 8. All right. So and your line actually should go from that point through all basically nodes of your grid lines. So make sure you put it correctly, and because in this sort of problem, the precision of drawing actually will influence on your solution and your time saving, because from there you need to be able to define integer points. Okay, so we set up line 3, so we mark as a line 3 and say, okay, that's line 3 with an equation x plus y equals 8. And because we set up inequality x plus y less or equal than 8, so if you transfer x to the right side, you'll see that y should be less or equal than negative x plus 8. So I'll show you one more time how to do that. So if you transfer x to the right side of the inequality, you'll get negative x plus 8. That means this is your line 3 equation, and your y satisfied for that inequality should be less or equal. So the region actually is just simply below this line. Okay, so right now we set up the triangular region if we're talking about line 1, line 2, and line 3, and all those inequalities, the first 3. Okay, so let's set up line 4, which have the following inequality. Y is less or equal than minus 2x plus 12, or for the line, actually we need to have an equation. So y equals negative 2x plus 12. Okay, and here we are going to again set up xy table so that to get some values. So actually 2 points is pretty enough. But here is the trick, what I'm going to do right now, because definitely I'm sure that line 4 will intersect with line 3. I'm going to define the points of intersection between them. So actually what I'm going to do right now is better if I equate line 4 and line 3. So basically, let's say y's. So if I equate with line 3 for y, which is negative x plus 8, and I equate y's, I'll find the point of their intersection. So I'm looking for intersection point for line 3 and line 4. Okay, so let's try to do negative 2x plus 12. That's y for line 4 will be equal to negative x plus 8. From where I can rearrange and solve in terms of x. So transfer negative 2x to the right side, I've got x, and 12 minus 8, I'll get 4. So when x is 4, I'll get the point of intersection. So actually x is 4 is here. So, and I need to find y as well. So I plug, for example, into equation of line 3, negative 4 plus 8, I'll get also 4. So obviously that's going to be the point of intersection of those two lines. So I've got 1 point, 4 and 4 for line 4. Okay, so that's why in terms of the table values, I've got 1.4 and 4. So considering that equation for line 4, what I'm going to do, I'm going to just plug any x point, or probably I can set up y equals 0, it's easier. So to find x-intercept in this case, so I'll get the following. I'll get that x equals to 6. So we've got another point, 6 and 0. 6 and 0, that's another point. And I set up the line that goes through 4, 4 and 6, 0. Let me try, not so accurately, sorry. So I just trying to put this line right like that, okay? So this is the line that goes through the point, and equation for that line, which is L4, is 2x plus y equals 12. Okay, so I've set up all the lines, and now I just want to highlight the region for line 4 and for inequality that 2x plus y less or equal than 12. So I indicate that region here inside. Okay, so I've got it, and hence I've got the region that looks like quadrilateral. 1, 2, 3, 4, 4 sides. So instead of arrows right now, I'm gonna probably use the marker. Let me try to use the marker. If I use that, it's interesting for me. Will it work? For example, purple one. So I indicate the region, or probably I can put the letter R just inside. Not so really good because actually, okay, so what I'm gonna do, I'm just try to make shadings there inside. Okay, so I use, let's say, that greenish one, and just what I'm gonna do, I want to shade the region that is gonna be a solution for the problem 1. Okay, so that's the region. I'm not gonna set up R letter inside because I'm not gonna do that because right now, let's have a look at the problem 2. How many points in R will have integer coordinates? So that means right now what I'm gonna do, I'm going to count all the integer points. So instead of counting, I just simply put them and say, okay, use that one in order to indicate all the integer coordinates and integer points within the region R. So our region is shaded with the green one. Okay, so right now I'm going to do that, and so that's the boundary, not the primary color, sorry. So yeah, so boundary, 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 okay. So I moved along the boundary and mark all the points. So next one, also within the nodes. But first let's go along the boundary. So along the boundary of line 3. So what I see here, actually it's not drawn accurately, but I know that this line is sort of identity line that goes with negative gradient shifted 8 units up. So actually those values are integers because they're in the nodes of the cell. Okay, so perfect. Oops, sorry, my bad, actually I went wrong. So that's the last point on that line, so because my region next goes along that line. So here what I clearly see is definitely that point only. So you can check, like, at this point adhere to the graph, adhere to the line 4 or not. So you can simply plug x equals 5 and you should get y equals 2. So let's do it. Yeah, so if you plug y be equal to 2, so that means it works. So that's why that's going to be an integer point. Okay, so we mark all the points along the boundaries, and now we need to also fill it with internal region and integer points as well. So they are here. Okay, that's the whole set. So actually they need to be filled in. However, there is the problem with software. So if I trying to hold the marker, hold the pen and stylus right and hold for a second, it don't mark and it doesn't put the dot actually. All right, so we've got all the points. If you like, you can count, so but they're integer points within the region. Okay, so we answered part 2. So guys, I need to actually erase some unnecessary workings here because right now I'm going to clean the space for further consideration. So hope you got it until so far. So what I'm gonna do right now, I'm going to solve the third part of the problem, and here's what we're actually looking for. So in problem 3, you need to find all integer coordinates x and y such that the function 2x plus y equals 12. So basically the coordinates need to satisfy that equation of the line. So 2x plus y, this basically comes from 2x plus y less or equal than 12. This is line 4. So actually right now we are looking, so that's question 3. So we're looking for the values. So on question 3, we're looking for the coordinates x and y so that they, first of all, adhere to the region, of course, and that also from the equation of line 4, which has an equation 2x plus y equals 12. So 2x plus y equals to 12, okay. And from the line 4, which has an equation 2x plus y equals to 12. All right, so let's first of all highlight this line, so it's right there. I just make it bold. Wow, interesting. It's really bold. Okay, so this is line 4. And right now what I'm gonna do, I'm gonna just simply state the coordinates of all integer points within the region and adhere to the line. So actually only those 3 points, so that's why I just list them. So the first is the point, okay, I just show it right here. So the first coordinates, it's 4 and 4, so 4 and 4. So the second one is here, is 5 and 2. Okay, and the last one is 6, 0, so it's right there, 6 and 0. All those 3 coordinates should satisfy an equation. You can just plug instead of x, y coordinates 4, 4, 5, 2, and 6, 0, and actually check that the resulting value should be equal to 12. Okay, but I'm pretty sure because all the points are on the line. They're only integer points, of course. There are actually infinitely many points within this segment. However, we're looking for only integer points. All right, so that's how to cope with this third type of questions here. Okay, and the last one, problem 4. So problem 4 is pretty interesting because you need to find the max value for the expression 2x plus 3y, where x, y are from our region and they have integer coordinates. Okay, so 2x plus 3y. In linear programming, 2x plus 3y, it's an objective function. So basically we can say that this expression is equal to, let's say, z, and instead of z, so what we understand under z. So this is an objective function that we are going to optimize. What does mean optimize? We might look for the maximum or minimum value. In this case, we need to find the max value, so we're going to maximize that and find max of z, okay? So maximum value of z, 2x plus 3y. Looking at the lines from our set of inequalities, line 1, line 2, line 3, line 4, so it's completely different expressions. So that's why our function 2x plus 3y goes somehow in a very different way. So it might go depending on z value because z is some number. So 2x plus 3y is going to be a linear function. Yes, and because z is a number, so it will be equal to some z. So that's simply the general equation of some line that goes within the region, because x, y coordinates should be from the region. So they must adhere to the region. Okay, so how to solve, how to maximize? There is the theorem that tells you actually the following. Your R, your region here, it's a feasible region. Basically, it should represent the convex polygon. So convex means that if you take any 2 points within the region and even on the boundaries and connect them, this segment will completely lie within the region R. So it means, for example, I can show you the way how to draw polygon that is not convex. For example, what I'm saying, if you take any 2 points, for example here, and connect them with the segment line, you see that part of the line or part of that segment actually beyond the boundary. So in this case, this polygon is not convex. However, if you try to do it here, so you can get all segments of that, all parts of the segment connecting any 2 points within the region. So that's why this region is convex. So your R actually is convex polygon, and in this case Z is going to be an objective function that you want to maximize or optimize somehow, find the maximum or minimum value. Okay, and when Z has an optimum value, so you're pretty sure you know that, so it means that the optimal value of that function must occur at the vertices of that region. So vertices is exactly there, like vertices of the polygon. Basically, they are corner points. Okay. However, in this case, we're not really sure does Z function has an optimal value or maximum or minimum. So we don't know. So that's why we're going to use another theorem that helps us to figure out about where max and mean values occur at which points. Okay, so that's theorem, the second theorem that actually tells us that if R is the region, feasible region for linear programming problem, in our case that's linear programming problem definitely, so your function Z as an objective function is bounded. So what does it mean bounded? It means it represents an enclosed area. So if you can circle this area and so that the whole region will be within the circle, so that means you have a bounded region. Okay, so in this case, the bounded region that we have right now, and theorem tells that objective function Z will have both max and means, so it will have the optimal value max, both max and means, maximum and minimum, at the corner points or at the vertices, at the vertex points of region R. Okay, so we've got that, and in this case, so look, we're looking for the maximum. So how many boundary, how many vertex points we have? So let's just name them or list them. So the first is that 0, 0. So that's one vertex. Actually, I highlight them a little bit. So that's the first, that's the second, that's the third one, and the last one, actually that one. So we've got all red points that are vertex points. In this case, that's vertex 1, it's here. So next one, vertex 2, actually 0, 8, 0, 8. Vertex 3 is 4, 4. And vertex 4 is 6 and 0. So what are we gonna do? According to Cerium, our region is bounded. We just need to test which value deliver us the minimum or maximum. In this case, we're looking for a max value. So which vertex delivers the maximum value for the objective function. Okay, so let's try to do it. So let me zoom out a little bit. So right now we got that here, okay? And just we need to plug all those points to calculate z. Okay, so if we plug 0, 0, obviously z will have 0 value. If we plug 0, 8, so we'll get 24. Z is 24 in this case. If we plug 4 and 4, so we'll get 4 times 2 is 8, 3 times 4 12, so we'll get 20. So obviously right now 24 is the highest value, and it occurs here at the vertex 2. So, and the last what we're going to plug is 6 and 0. So that's the vertex 4. And if we do that, we'll get only 12 here. So z will be equal to 12. So make sure you understand how it works. So looks like z is going to be 24, and that's going to be the highest point. So what if we just simply draw the graph of the line? So 2x plus 3y equals to 24, because right now instead of z we've got the number. So one more time, so 2x plus 3y equals to 24. So right now we've got z equals to 24, and just actually we can show how this line goes. Okay, so 2x plus 3y, so let's set up. So we just simply can take x equals 0. In this case, y is going to be 8. So that's one point. And the second point, we can plug y equals 0. In this case, x is going to be 24 over 2, which is 12. Okay, 6, 8, yeah, we'll change the scale actually. So 12 is going to be somewhere here, I guess. So just plus 4. So 3. So I guess, yeah, it's going to be somewhere. So 4 is here. Yeah, 3 cells. So that's going to be 12. And if we connect with the line, okay, let's say the green line for our function that we've got. So we've got that line that will go this way. So it's going to be line for our optimal solution, 2x plus 3y equals, in this case, 24. And as we can see, it has only one common point with the region where actually the maximum value occurs. Okay, if you take any other points on the line, that will give also 24 for z, but they're actually beyond the region. So that's why we have only one common point of this objective function with the value 24 with our line, with our region. So that's why only there in the coordinates 0, 8, the maximum value for z, which is 24, occurs. So if you want to test all the values, let's say you can test any other points within that region, and you see that maximum value cannot be reached by our z objective function. So definitely you can check by your own, so you can test. So that actually was complete, I think, manual how to cope with this sort of problem when you have integer points and you're looking only for integer points. So in the next video, I'm going to show you how to solve some applied problems would actually be within manufacturing. So we can classify those problems as manufacturing, as sort of like diet problems. And actually we can also, if we go to logistics, about transportations, So we can say that the third category is going to be transportation sort of problems dedicated to how to transport effectively using specific like schedule. Okay, so hope you like that, guys. That was complete manual for inequalities. I'm pretty sure that you need to start from the very beginning if you're new for that topic, if you want to understand how it works. So guys, encourage you to start from the very first video when I explain the basics and go up to here, because that at this stage is pretty more complicated for you, might be for most guys who first see that. So actually just roll back and start all over again to watch all those videos, and come in here, you'll have enough theoretical basis in order to accomplish this task. Okay, so thank you. That was Daniel Dallas. Peace out.